Good evening. We know far more about Mercury and Venus than since the dawn of the space age. The region between the orbits of Mercury and the Sun is frequently visited by comets, and on occasions these can be seen falling into the Sun on images beamed back from NASA's SOHO spacecraft. Other comets simply disintegrate, like that of Ison in January 2014. So there is plenty of rocky debris around to impact on the planet Mercury to form craters. And on rare occasions, very large impactors arrive, one of which created the Colaris Basin, one of the largest impact basins in the solar system. While another hit Venus hard enough to turn the planet upside down. The planet Mercury is named after the Roman god Mercury, the messenger carrier, with winged sandals. It is the closest planet to the Sun, lying at a mean distance of 57.9 million kilometres, speeding along its orbital path at more than 47 kilometres a second. In terms of size, it is not much bigger than our Moon, and its appearance is very similar. Mercury is 4,880 kilometres in diameter and is mainly covered with impact craters. A day on Mercury is 58.6 Earth days long, which is slightly less than the planet's year of 87.9 days, which makes it synchronous, just like our Moon, which always keeps one face turned towards the Earth. Mercury is gravitationally locked and rotates in a way that is unique in the solar system. As seen relative to the fixed stars, it rotates exactly 3 times for every 2 revolutions it makes around its orbit. As seen from the Sun, in a frame reference that rotates with the orbital motion, it appears to rotate only once every 2 Mercurian years. An observer on Mercury would therefore see only one day every 2 years, which makes the calendar very strange indeed. There is no area of permanent daylight, no region of permanent night, and no twilight zone. Since Mercury is so small and close to the Sun, it is generally hard to find either in the dusk sky after sunset or the dawn sky before sunrise, even though its magnitude can equal that of the brightest stars. Also, its maximum angular diameter can never be more than 13 arc seconds when it is at its best, when the planet is closest to the Earth, at about 82.5 million kilometres. Therefore, Mercury is a telescopic disappointment, since large telescopes are needed to glimpse any detail on the planet, although its phases can be viewed in moderate-sized telescopes. Much of what we know about Mercury comes from images and observations sent back by 2 NASA spacecraft. Mariner 10, which was launched on the 3rd of November 1973 and flew past Mercury on 3 occasions at an average distance of 200 kilometres. Twice in 1974 and again on the 16th of March 1975, along with the Messenger mission, which is due to come to an end soon. Mariner 10 was a mission of many firsts. It was the first spacecraft to visit Mercury, the first to use a gravity assist, and the first to visit more than one planet. Mariner 10 passed Venus on February the 5th, 1974. I will have more to say about this later in the programme. It was also the first to make multiple flybys of a planet, in this case Mercury, and the first to use the solar wind for orientation during its flight. Owing to the geometry of its orbit, the same side of Mercury was sunlit each time, so Mariner 10 was only able to map 40 to 45% of Mercury's surface, taking over 2,800 photos. It revealed a more or less moon-like surface. It thus contributed enormously to our understanding of the planet, whose surface had not been successfully resolved through telescopic observation. Mariner 10 also discovered that Mercury has a tenuous atmosphere consisting mainly of oxygen, 42%, as well as a magnetic field and a large iron-rich core. The atmosphere of Mercury is essentially a vacuum. Composition values are variable and the values are not well controlled. This is due to the Sun's heat constantly changing as the planet orbits around the Sun. At perihelion, Mercury is 46 million kilometres distant from the Sun and 69.8 million kilometres at aphelion, a difference of 23.8 million kilometres. This affects the planet's overall temperature and the density of the thin atmosphere. Sunlight and the solar wind constantly blow away Mercury's atmosphere into space. It therefore also depends on whether the Sun is at solar maximum when the number of flares are at their greatest, as they are at the moment. This affects the level of solar wind streaming over the planet. Mercury's thin atmosphere contains oxygen, hydrogen and helium, along with smaller amounts of sodium, potassium, calcium and magnesium. Mercury's density is the second highest in the solar system, at 5.4 grams per square centimetre, only slightly less than the Earth's density. Mercury's density can be used to understand details of its inner structure. Although the Earth's high density results appreciably from gravitational compression, particularly at the core, Mercury is a much smaller planet and its inner regions are not as compressed. Therefore, for it to have such a high density, its core must be large and rich in iron. Geologists estimate that Mercury's core occupies about 42% of its volume. For Earth, this proportion is 17%. Research published in 2007 suggests that Mercury has a molten core. Surrounding the core is a 500 to 700 kilometre mantle consisting of silicates. Based on data from the Mariner 10 mission and Earth-based observations, Mercury's crust is believed to be 100 to 300 kilometres thick. One distinctive feature of Mercury's surface is the presence of numerous narrow ridges, extending up to several hundred kilometres in length. It is believed that these are formed as Mercury's core and mantle cooled and contracted at a time when the crust had already solidified. Mercury's core has a higher iron content than that of any other major planet in the solar system, and a number of theories have been proposed to explain this. The most widely accepted is that Mercury originally had a metal-silicate ratio similar to chondrite meteorites, thought to be typical of the solar system's rocky matter, and a mass approximately 2¼ times its current mass. Early in the solar system's history, Mercury may have been struck by a planetary body several thousand kilometres across. The impact would have stripped away much of the original crust and mantle, leaving the core behind as a relatively major component. A similar process, known as the giant impact theory, has been proposed to explain the formation of the Moon. The radiometer readings of Mariner 10 suggested that Mercury has a nighttime temperature of minus 183 degrees centigrade and a maximum daytime temperature of plus 187 degrees centigrade. Mercury's surface is similar in appearance to that of the Moon, showing extensive mare-like plains and heavy cratering, indicating that it has been geologically inactive for billions of years. Because our knowledge of Mercury's geology has been based only on the 1975 Mariner flyby and terrestrial observations, it is the least understood of the terrestrial planets. Mercury was heavily bombarded by comets and asteroids during and shortly after its formation 4.6 billion years ago, as well as during a separate subsequent episode called the Late Heavy Bombardment that came to an end 3.8 billion years ago. During this period of intense crater formation, the planet received impacts over its entire surface, helped by the lack of any atmosphere to slow impactors down. During this time, the planet was volcanically active. Basins such as the Calaris Basin were filled by magma, producing smooth plains similar to the Maria found on the Moon. Data from the October 2008 flyby of Messenger gave researchers a greater appreciation for the jumbled nature of Mercury's surface. Mercury's surface is more varied than either Mars or the Moon's, both of which contain significant stretches of similar geography, such as Maria and plateaus. NASA's spacecraft Messenger was launched in August 2004 to study Mercury's chemical composition, geology and magnetic field. It became the second mission after Mariner 10 to reach Mercury when it made a flyby in January 2008, followed by a second flyby in October 2008 and a third flyby in September 2009 before entering Mercury's orbit in March 2011. On the 3rd of July 2008, Messenger team member Thomas Zurbuchen announced that the probe had discovered large amounts of water present in Mercury's slight atmosphere, which was an unexpected finding. Messenger also provided visual evidence of past volcanic activity on the surface of Mercury, as well as evidence for a liquid planetary core. Messenger's formal data collection mission began on the 4th of April 2011. By the time the primary mission was completed in March 2012, close to 100,000 images had been returned to planetary scientists. On the 5th of October 2011, the scientific results obtained by Messenger during its first 6 terrestrial months in Mercury's orbit were presented in a series of papers at the European Planetary Science Congress in France. Among the discoveries were the unexpectedly high concentrations of magnesium and calcium found on Mercury's night side, and the fact that Mercury's magnetic field is offset far to the north of the planet's centre. In November 2012, NASA reported that Messenger had discovered both water ice and organic compounds in permanently shadowed craters at Mercury's North Pole. In February 2013, NASA published the most detailed and accurate 3D map of Mercury to date, and assembled from thousands of images taken by Messenger. Craters on Mercury range in diameter from small bowl-shaped cavities to multi-ringed impact basins hundreds of kilometres across. They appear in all states of decay, from relatively fresh rayed craters to highly ruined crater remnants. Mercury's craters differ from lunar craters in that the area blanketed by their ejecta is much smaller. This is a consequence of Mercury's stronger surface gravity. The largest known crater is the Calaris Basin, with a diameter of 1,550 kilometres. The impact that created the Calaris Basin was so powerful that it caused lava eruptions and left a concentric ring over 2 kilometres high surrounding the impact crater. At the antipod of the Calaris Basin is a large region of unusually hilly terrain known as the Weird Terrain. This antipod is the point on the planet's surface directly opposite the Calaris Basin. One theory for its origin is that shock waves generated during the Calaris impact travelled around the planet, converging at the basin's antipod 180 degrees away. The resulting high stresses fractured the surface. Alternatively, it has been suggested that this terrain formed as a result of the convergence of ejecta from the Calaris Basin itself. Overall, about 15 impact basins have been identified on the imaged part of Mercury. A notable basin is the 400 km wide multi-ring Karlstag basin that has an ejecta blanket extending up to 500 km from its rim and a floor that has been filled by smooth planes of material. Like the Moon, the surface of Mercury has incurred the effects of space weathering processes, including solar wind and micrometeorite impacts. MESSENGER achieved 100% mapping of Mercury on the 6th of March 2013 and completed its first year-long extended mission on March the 17th, 2013. Its second extended mission is scheduled to end later this month. Seen here, under construction in January 2015, is the next mission to study Mercury. Called the Bepi-Colombo mission, it consists of two separate orbiting spacecraft, the European Space Agency's Mercury Planetary Orbiter, MPO, and the Japan Aerospace Exploration Agency's Mercury Magnetospheric Orbiter, MMO. Mercury Planetary Orbiter will study the surface and internal composition of our solar system's innermost planet, and MMO will study Mercury's unusual, powerful magnetosphere, the region of space around the planet that is dominated by its magnetic field. The twin orbiters will also search for more signs of possible water ice in some of Mercury's permanently shadowed craters. That is all we have time for this month. Please visit our website, Vimeo, where you can watch all of the past shows of astronomy and space. And if you like this program, please share it with your friends and members of your local astronomical society. Until we come back next month, good evening.